Previous to this, we've looked at what? Increasing, decreasing functions, the extreme value theorem, relative minima and maxima, the first derivative test, the second derivative test. All of this was to give us a picture of what functions are doing at different places. Well, section 3.5 is no different. We're talking about, well, what's happening out on the ends? And so in previous classes, you might have heard the term end behavior. All that really means is what's going on when x is getting further and further to the positive end of the number system and further to the negative side of the number system. In other words, positive infinity and negative infinity. What's going on there? So as we're going through this, it's important to remember we don't care so much what's happening close to the y-axis or even a little further out from that. What we're interested in is what's going on as x approaches positive infinity and negative infinity. The function we're looking at here is this one. And the table shows what's happening as we go further and further in the negative direction and further in the positive direction. We've done something similar to this when we were talking about limits before. Well, we're talking about limits again, and look at the notation. This says, as x is approaching positive infinity, then that function that we're looking at approaches the number 3. Now notice, it's never getting to 3. That 3 is a limiting line that it's not going to cross. And another way of saying this is, as x is approaching negative infinity, well, that function's still approaching 3. Here's a technical definition of what's going on. The limits at infinity, kind of a misnomer because we never reach infinity. This is always as x is approaching infinity. And it looks a whole lot like the definition of limits that we've seen before. Then the second box is telling us about horizontal asymptotes. The important thing to take away from that is, at most, we can have 2 of these horizontal asymptotes, one on the left and one on the right. And sometimes those are going to be different. So we're holding on to all the material that we learned about limits. We're just adding to it. So this theorem, 3.10, is talking about limits at infinity. First of all, r, the exponent in the denominators here, has to be a positive rational number. C, on the other hand, is any real number, positive, negative, whatever. Look at the first part. It says no matter what C is, as the denominator is getting bigger and bigger, in other words, x is approaching infinity, this whole fraction's limit is 0. Well, that makes sense. And the bottom here is reminding us that it really doesn't matter if the denominator is positive or negative. That when you've got some constant like c divided by a really large number, that fraction approaches 0, no matter what the sign of the denominator. Keep that in mind. That's real easy to mess up on. That's why I put a star by it. So let's take a look at the end behavior of these two functions. Remember, end behavior is what's going on when x is approaching infinity and what's going on when x is approaching negative infinity. Here's my function. I know that I can split those limits between the 5 and the 2 divided by x squared. And then let's take a look at what we've got. I know from previous experience that the limit of 5, that's a constant, is just 5. There's no x involved, so 5 is just plain old 5. The second part of that, though, look what we've got going on. We've got some number, in this case 2, divided by x squared. Well, what's going to happen is x gets bigger and bigger and bigger in the positive direction. that fraction is going to hit a limit of 0. So the limit for this whole function as x is going in the positive direction is just 5. Let's look and see what happens when x is going in the negative direction. Remember, we might get two different answers here. Well, 5, the limit of 5 is just 5. And even if x is a negative number, we're squaring it. And that means our fraction is getting closer and closer and closer to 0. So our end result is this. Here's the graph of that function. Notice 5 is the horizontal asymptote. And we're not worried about what's going on in here. We are concerned with as x approaches infinity and as x approaches negative infinity. Well, we can see from just this part of the graph that our function is getting closer and closer and closer to 5, no matter which direction we're going. Taking a look at the second function here, a little more complex than the first one. I'm going to give myself a little more room here. I'm going to use an algebra trick. I'm going to multiply the top by 1 over x and the bottom by 1 over x. I'll show you why here in just a second. Look what that gives us. On top, I've got this. On the bottom, I've got this. Now remember, I can split numerators. So on top, what I'm going to do is I'm going to combine the 2x and the x and the 1 and the x. All I did was split numerators. The denominator x stayed the same. Then on the bottom, same kind of thing. Now what did that gain us? I can do this. This gives me a 1 down here. And then I'm going to look at what I've got left, those fractions. What's happening? I've got a constant divided by x. And as x is getting bigger and bigger and bigger, what's happening to my whole fraction here? This is going to 0, and that's going to 0. Doesn't leave much. So the limit as x is approaching infinity is just 2. Would that change any as x approaches negative infinity? No, it's still just going to be 2. Let's take a look at the graph of that. We've got our limit, y equals 2, and we can see how our function's taken off as x is approaching infinity and negative infinity. It's getting closer and closer to that y equals 2 line, but it will never reach it. Can you have infinity divided by infinity? Yeah. And it's another indeterminate form. We've seen that before with 0 divided by 0. Man, we had to do something. Look at the guidelines when we have limits at infinity. If the numerator has a degree that's less than the denominator, then the limit of the function is 0. In other words, the x-axis. So if I had something like 3x divided by x squared, the degree of this top up here is 1. So I would have a horizontal asymptote, in other words, a limit of the x-axis for that function. Number 2, if the degree of the numerator is equal to the degree of the denominator, then the limit is just the ratio of the coefficients. What does that mean? What if I had 4x cubed, and plus some more stuff out here on top, and I had 3x cubed plus some more stuff here? This is saying just take these coefficients. The limit would be 4/3. We've seen that before. We just didn't realize it. Look at this function over here, this one. I've got 2x minus 1 divided by x plus 1. All I got to do is just take the leading coefficients because the degree of the top is the same as the degree of the bottom. So I could have just gone like that. And that's exactly what we ended up with down here. Finally, if the degree of the numerator is bigger than that of the denominator, the limit doesn't exist. Now, if you remember from college algebra and maybe pre-cal, if that situation occurred and the numerator was 1 more than the denominator's degree, then we had a slanted asymptote, an oblique asymptote. Here, since we're talking about limits, we just go, the limit doesn't exist. And the highlighted stuff at the bottom is just reminding you that the biggest rules in this case, the largest power of the variable is the most important part as that variable gets larger. That's why we've got these rules. It controls everything. Now we're going to use similar techniques to what we used with problem 1a and 1b. This one is just a little more complex. First thing I'm going to do is give myself some more room here. Now before I would have said, let's multiply the top by 1 over x and the bottom by 1 over x, but we've got a square root on the bottom. So I can still say, let's multiply the top by 1 over x. But here's where you have to think about it. In the bottom part, I've got 2x squared. Forget about the 1 for just a second. If I've got x squared inside a radical and we're going in a positive direction, we're going as x approaches positive infinity, then couldn't I do this? And in that case, aren't the top and the bottom the same if we're going in a positive direction? Take a second and think about that. So what does that give me? This is my numerator, again, just like problem number 1, and here's my denominator, except it's under a radical. Okay, so far so good. Now if you remember what we did in problem 1, we split the numerators in both cases. So I've got 3x divided by x, 2 divided by x in my numerator. The denominator, what's that going to give me? Well, something similar, it's just under a radical. Next thing we do is cancel out the x's in the numerator and the x squares in the denominator, which leaves us this. That 2 divided by x goes to 0. That 1 divided by x squared goes to 0, because remember, we're going towards infinity. So those two fractions approach 0. What's that going to leave us? This. Part B is serving as a reminder to us that we might have different limits as x approaches infinity and x approaches negative infinity. Just looking at that fraction, if x is a negative number, the numerator is going to be negative. What would the denominator be? It's going to have to be positive, right? Because we're squaring the x inside the radical. So let's start off like we did before. And I'm going to treat the top like I did before. But the bottom, I've got to think about that. If x is negative, then the top's going to take care of itself because I'm multiplying by 1 over a negative number. So that's going to work out okay. But the bottom is going to be positive. So here's what I have to do. I can still say this, but I've got to say, all right, that might end up being negative. So I'll put a negative sign out front. I'm getting the same thing I did in the numerators before, but remember, we're going toward negative infinity. So our x values are negative. So the only thing different in between this one and part A is that negative sign out front of our denominator. This looks the same. The denominator, except for the negative sign, looks the same. I cancel. I think you can see where this is headed. These two fractions both go to 0, which is going to leave me this. Notice that is a different limit from part A. Let's see what it looks like. Now we have two limits. Our top limit is the green line. Our lower limit is the blue line. But notice our function never crosses those lines. Are we worried about what's going on in here? No. It's only as we're approaching positive infinity and negative infinity that those limits really come into play. That's why they call this end behavior. What's happening at the ends of our function? So remember this trick that we did right here. That negative sign had to be there. Not all functions reach a nice limit of 3 or 3 over the square root of 2 or a number. Sometimes that function is going to increase or decrease without bound as x gets larger or smaller. The highlight says, especially for polynomials, that end behavior is determined by two things: the sign of the coefficient and whether we're talking about an even or odd exponent. As we're looking at these infinite limits at infinity, that means our function is either going to positive infinity or negative infinity. Again, our y values are either going to positive infinity or negative infinity. Look at the notation here. In both these cases, we're talking about as x is approaching positive infinity. So don't worry about the technical stuff so much. What does this mean? Well, the first part says, as x is increasing, y is increasing. So as x approaches positive infinity, so does y. That's one situation. Another one is here, which says as x is increasing still headed toward positive infinity, y is decreasing. In that case, the limit would be negative infinity. And in the box here, please remember we could do something similar for x approaching negative infinity, and we could see what the y's are approaching. Let's look at x cubed as x is approaching positive infinity. What's happening? X is getting bigger without bound. What's y doing? Pick any positive number x and cube it. Y is getting bigger and bigger. So we could say that the limit as x approaches infinity of x cubed is positive infinity. So x is going to positive infinity, so is y. Contrast that with the limit of x cubed as x is going the other direction. It's getting more and more negative. So we're talking about cubes here. Pick a negative number and cube it. That's going to be a negative number. So as x is headed toward negative infinity, so is y. So what would this limit be? Negative infinity. Just to make sure we understand this part B, what if I had the limit as x approaches negative infinity of x to the fourth? So pick a negative number and raise it to the fourth power. You're going to get a positive value. So in this case, x is approaching negative infinity, so it's getting more and more negative. Just like before, but what's happening to our y's? They're getting more and more positive. So here we'd say this limit, as x approaches negative infinity, is positive infinity. And that's what the notes we're talking about up here. The end behavior for these polynomials is determined by the sign of the coefficient and whether that largest exponent is even or odd, like we just saw here. Difference between x cubed and x to the fourth, when we're talking about x approaching negative infinity. And just for good measure, here's a graph of y equals x cubed. We can see as x increases toward positive infinity, our y's are increasing toward positive infinity. As x is decreasing toward negative infinity, our y's are decreasing toward negative infinity. And that's what we found back here. All right, so we added something else now. We're talking about limits as the x values of our function approach infinity. And those limits could be actual numbers, or as we just saw, those limits could be infinite also.